Okay, so we have a beam that is submitted to a distributed load W, and we know the value of W. We know that W is 3 kilonewton per meter. And the question is, what are the reactions at A and B? So first, let's replace this distributed load by one load that will be in the middle. And it will be equal to 3 times 4. It will be equal to 12 kilonewton. And that will be at 2 meters from both sides. But we will use the moment from B. So let's put it this way. And the reactions are there. We have normal force only, NA, on this little cylinder. And this is a pin connection. So we have a B, Y. And because NA is going to the right, we will have BX going to the left for sure. I can write my axis X and Y there. Okay, and the question is, what is NA, BX, and BY? So the strategy is to use the moment about the pin connection most of the time. So sum of the moment about B equals 0 because BX and BY will not be included inside the equations because they are going through the point B. So the 12 kilonewton tend to rotate in the positive directions, 12 times the distance perpendicular, that is 2. Now for NA, we have different options to find the moment about NA. Let's use the vertical complement and horizontal complement of NA. Okay, we have 30 degrees, and that's the same 30 degrees there. Okay, so for the vertical complement, let's write everything in green. So we have, and it's tend to rotate in the negative directions. So minus NA cosine 30, and the distance is this one. So the distance will be 4 plus 3 cosine 30. Okay, so that's the total there. So the 3 cosine 30, that's this one, and the 4, that's this one. And now for the horizontal complement, so I will draw everything related to the horizontal complement in purple. It tends to rotate in a negative direction about the point B. So we have minus NA. The complement is sine 30. And the minimal distance is this vertical distance. So that's the 3 times 3 sine 30 again, because that's this distance. And everything is equal to 0. So we have 24. That is equal to, I will factorize by NA. So we have cosine 30 times 4 plus 3 cosine 30. And that's inside the NA. I switch both on the other side. So that's plus everywhere. So plus sine 30 times 3 sine 30. There. So we can find NA. That is equal to, oops, let me try to write everything. So cosine 30 times 4 plus 3 cosine 30 plus the 3 sine 30 square. So we got NA. Let's plug everything in the calculator. 24 divided by, don't forget to add your parentheses there on your calculator. Cosine 30 times, oops, time 4 plus 3 cosine 30. Take your time to not make any mistake. Plus 3 times sine 30 times sine 30. Oops, oops. That's it, 3.71 kilonewton. That's for NA. And we have to solve now for BX and BY. Let's do BX first because there's just NA. So we have sum of the forces on X is equal to 0. So we have NA sine 30 at the purple complement. minus Bx that we guess that will go to the left, that we guess, but we know it was going to the left. There's no other possibility. So Bx is equal to Na 3.71 sine 30. Oops. So this one, sine 30. 1.186 kilonewton. And we will use the force on the y. So sum of the force on the y equals 0 for By. So we have Na cosine 30 for the green complement minus 12, the distributed load, plus By is equal to 0. So we have By that is equal to 12 minus Na, that is 3.71 cosine 30. So 12 minus the value of Na and cosine 30. This is 8.78 kilonewton. Here we go. Let me highlight the answers. So we have the Na, the Bx, and the By. And if you want to know the magnitude of the complement in the pin connection at B, you do B equal to square root of 1.86 square plus 8.78 square. So this is 1. Take your exact value in your calculator. Square plus this one square. That's 8.98 kilonewton. Here we go. That's the magnitude of the force in the pin, inside the pin. So that's it for this little example with an easy distributed load and the reaction force to find, and the force to at the reaction, and the force of the reactions at the connections at A and B to find. Bye bye, see you in the next video.